Hey everybody. Today we're factoring higher degree polynomials using the rational root theorem and the factor theorem. The process for factoring higher degree polynomials is always the same. Find a root, that gives you a factor, then use long division to get a lower degree polynomial. Then you just repeat that process until you can't go any further. So as we go through that process, we're using two key theorems. Let's just state them right up front. First of all, the factor theorem. A polynomial has a factor x minus c if and only if c is a root of the polynomial. The second result we're going to use is the rational root theorem. It's a bit of a mouthful when written in all of its generality. Here it is. I want to focus here on the version that we typically use when we're doing actual problems. And that focuses on the case where we have a monic polynomial. Something of this form. A polynomial where the leading coefficient is just 1. So if you look at the x to the n here, notice there's no a sub n in front of it. In that case, the rational root theorem just says that the only possible rational roots are integers that are factors of the constant term, a sub 0, possibly negative. I think this all makes more sense when we actually do an example problem. So let's work through this. Factor the polynomial completely, x to the third minus x squared minus 4x plus 4. As we do that, we're going to find all the rational roots. So according to the rational root theorem, the only possible rational roots of this polynomial are going to be the integers plus or minus 1, 2, and 4. So I'm looking at that constant term, 4, and taking all of its factors, 1, 2, and 4, and doing plus or minus for each one. Now those are the only possible rational roots. To find out if they're actually rational roots, we have to plug in. So I'm going to just go down that list and literally plug them all into f. Now this is a degree 3 polynomial, so I can only expect at most 3 linear factors, x minus c. So there could be at most 3 roots counted with multiplicity, in other words with repetition. So let's start at the beginning. F of 1 is 0. That's a root. F of negative 1, on the other hand, is 6. That's not a root. Continuing on down the list, f of 2 is 0, so that's a root. F of negative 2 is 0, so that's a root. Hey, I've already got 3 roots. There can't be any more. But let's go down the other 2. Let's go through the other 2 just for completeness. F of 4 is 36. That's not a root. And f of negative 4 is 60. So that's not a root either. So far I've determined that x equals 1, 2, and negative 2 are all roots of this polynomial. And so by the factor theorem, x minus 1, x minus 2, and x plus 2 are all factors of the polynomial. Since it's a degree 3 polynomial, if there's any other factor, it has to be a constant. So the cubic can be factored like this, where c is some constant. Now, in this case, it's obvious that that constant has to be 1. If I FOIL out that right-hand side, the highest power term is going to be cx cubed. On the left-hand side, I have x cubed, so c just has to be 1. So overall, the factored form of the cubic is x minus 1 times x minus 2 times x plus 2. Let's do another example. Factor the polynomial 2x cubed minus 20x squared plus 24x plus 144. Now, in this case, we have a polynomial that is not monic. There's a 2 in front of the highest power term. However, that 2 is also a common factor for all the coefficients of the polynomial. We should start just by pulling it out. We're left with x cubed minus 10x squared plus 12x minus 72. So we want to focus on factoring that cubic. Now, unfortunately, 72 has a lot of factors. 1, 2, 3, 4, 6, 8, 9, 12, 18, 24, 36, 72. And any one of those could be negative. So we don't really want to have to plug in all 24 of those. Our strategy is going to be to plug in until we find one that is a root, and then use long division to simplify the problem. So hopefully we won't have to do quite that much plugging in. G of 1 is 75. That's not a root. G of negative 1 is 49. That's also not a root. G of 2 is 64. That's not a root. And G of negative 2 is 0. So we did find a root. Let's stop plugging in values there and switch over and do some long division. X minus 2 is a root, and therefore by the factor theorem, x plus 2 is a factor. So we want to do g of x divided by that factor x plus 2 to see what we're left with. I'm going to run through this long division. I'll explain it as I go. If you want to have a little bit more on long division, I'll throw a link up top to my video on long division. So to do this long division, I look at the highest power terms and I say, what do I need to multiply x by to get x cubed? The answer is x squared. Now I multiply x squared by x plus 2 and change the signs as I go. So negative x cubed minus 2x squared. Then I add and bring down the next term. Then I just repeat the process. What do I need to multiply x by to get negative 12x squared? And the answer is negative 12x. I multiply, changing the signs as I go, then add and bring down the next term. What do I need to multiply x by to get 36x? 36. So I multiply, change the sign, add, and now I'm done. I have a remainder of 0. And therefore this cubic, it can be written as x plus 2, the factor I started with, times x squared minus 12x plus 36, the factor I got after doing that long division. Now I'm down to a quadratic that I can factor just using my old school techniques. X squared minus 12x plus 36 is x minus 6 squared. Overall, I can factor my original cubic as 2 times x plus 2 times x minus 6 squared. One final example. Let's factor a fourth degree polynomial this time, a quartic. X to the fourth plus 7x cubed minus 7x squared plus 7x minus 8. This is a monic polynomial, so the only possible rational roots are going to be the factors of 8 there at the end, positive or negative. Let's plug in until we find one that's actually a root. We hit one right off the bat this time. F of 1 is 0, so that's nice. We don't have to do any more work to find a root. Now we know that x minus 1 is a factor of this polynomial, so we're ready to do some long division. Okay, let's do it. X to the fourth plus 7x to the third minus 7x squared plus 7x minus 8 divided by x minus 1. What do I need to multiply x by to get x to the fourth? X to the third. I multiply, changing the signs as I go, and then add. Bringing down the next term, 8x to the third minus 7x squared. I need to multiply x by 8x squared to get 8x to the third. Multiply, change the sign, and then add, bringing down the next term. The next is going to be plus x. Multiply, change the sign, add, and bring down the next term. I need to multiply x by 8 to get 8x. Multiply, change the sign, and then add. I have 0 remainder. And therefore, this fourth degree polynomial can be written as the cubic I just got, x to the third plus 8x squared plus x plus 8, times the linear term that I figured out before, the x minus 1 factor. So now I'm trying to factor a cubic polynomial. Let's call it g of x. X to the third plus 8x squared plus x plus 8. I want to find another integer root, so I look at plus or minus 1, 2, 4, and 8. G of 1 gives me 18. That's not a root. Negative 1 is not a root. 2 is not a root. Negative 2 is not a root. 4 is not a root. Negative 4 is not a root. 8 is not a root, but negative 8 is. So if I got lucky the first time, this time I got unlucky. But eventually I did find a factor, x plus 8. So I'm back to doing long division. That cubic divided by x plus 8. This time I won't run through all the steps. the result that you get when you do that long division is just x squared plus 1. And therefore, that cubic that I have, x to the third plus 8x squared plus x plus 8, is x plus 8 times x squared plus 1. And so my original fourth degree polynomial can be factored as x squared plus 1 times x plus 8 times x minus 1. So I'm down to 2 linear terms and a quadratic. Fortunately, that quadratic is irreducible. There's no way to factor x squared plus 1 just using the real numbers. I can tell that just by looking, for example, by noticing that the discriminant, b squared minus 4ac, is negative. So I really am done factoring this polynomial. It can't go any further.